Everyone, thanks for being here despite the nice weather. Pretty sure that it will be much more fun outside, but okay, I will try to entertain you for 1 hour and a half about dipole-dipole interactions between atoms. So this is a title. It's reasonably complicated and arrogant because, of course, I'm certainly not going to cover in depth any of these topics. But still, I will try to give you a few illustrations of how you can use dipole-dipole interactions between atoms in a way that I'm going to specify in the first lecture, and which is very connected to the lecture of Anna, actually. And so give you a few illustrations of how we can use them to do many-body physics, and also how you can use them to do some quantum information, and especially computing tasks. OK, so this week, you will hear a lot about dipole-dipole interactions. So there is a lecture of Anna. The lecture of Robin Kaiser will start tomorrow, and my set of lectures. And you'll hear those dipole-dipole interactions in various contexts. The first context, which is the one essentially covered by Anna and Robin, will be light scattering in the broad sense, actually. So either you scatter in a random ensemble of atoms, okay, and basically the question you ask is that, knowing the fact that when you send the light, you induce dipoles, and that if the medium is dense enough, those atoms may interact. What is the light that this sample scatters? And actually, this is a complicated question for exactly the reasons that Anna explained to you this morning, which is that you have a set of atoms. Each are two-level systems. So the power, the size of the Hilbert space is huge. And second, you've got the field, which has an infinite number of degrees of freedom. OK, so Anna also will explain you in the two coming lectures how you can arrange and tailor these interactions in order to do something useful in quantum optics. The second context in which you're going to hear about that is this set of lectures. So this is going to be what happens if you take your atoms, order them. So this is a fluorescence image of an ensemble of atoms. I will explain that to you more in details tomorrow. But for the moment, each dot here corresponds to one atom. It's a 2D pattern. And those atoms are separated by a few micrometers. So in principle, you can't do anything with them in the sense of interactions. However, if you excite them to Rydberg state, then the interactions become very strong, despite the fact that these atoms are very far from each other. And so essentially, they can interact, those atoms, those Rydberg atoms. Once again, I will explain you in more details what this is about. They can interact either via the van der Waals or the resonant interaction, and I will try to explain you what it is today. So why would you at all look at this kind of problem? Well, I mean, because we are doing what many other people do. We are trying to make in the lab artificial quantum matter. OK, so this picture is supposed to be a picture of me assembling atoms one by one. And there are actually two lies on this picture, two main mistakes. The first one is that this makes you believe that I'm actually doing something, which is totally wrong. I don't touch anything in the lab. And the second, the diamond makes you believe that we are very wealthy, and this is not the case either. OK, so why would you build this artificial matter? There are several motivations, and actually Anna gave some of them. And so I wasn't around last week, but I'm sure that you also had, in particular in the lecture of Jean-Michel, also some introduction to these topics. If you have artificial quantum matters, you can study interesting problems. One of them is the many-body problem that you encounter everywhere in condensed matter physics, because essentially the size of the Hilbert space is so large that it's very difficult to do any ab initio calculation on this system. So I'll come back to that more in detail tomorrow, but this is an example where if you build an artificial system, it can be a toy model for more complicated real-life problems like RITC superconductivity, for example. The second important thing is that if you have a machine which you design in order to produce some states of interest, entangled state, for example, those states may be of use for interesting applications. And one of them is quantum metrology. If you set an ensemble of atoms, at the moment the second is still defined using the cesium atoms, so take a collection of cesium atoms, and you assume that all of them are independent. So essentially, when you measure, the outcome of the measurement gives you a relative frequency of this clock transition, which goes like the inverse of the number of the square root of the number of atoms you have. Okay, so this is the ultimate, what is called the quantum projection noise, accuracy of an atomic clock. Now, if the atoms you were starting from, the ensemble of cesium atoms you were starting from, were not independent from each other, if the atoms were correlated in a way or another, for example, entangled or squeezed in a way which should be defined, then you may beat this standard quantum limit in order to enhance the sensitivity of the clock by a factor square root of n. So now in regular atomic clock, where you handle hundreds of maybe thousands of atoms, then you may expect a substantial gain. Okay, so and for this, you need to be able to engineer in the lab those states which exhibit correlations. And this is exactly what those synthetic matter or artificial quantum systems can do. Third application, obviously, you can also apply them for quantum information, because one of the essential ingredients of this quantum system, and I'll come back to that tomorrow, is that they exhibit entanglement. And entanglement can be used as a resource, either to perform secure communications, that I'm not going to touch, but to also try to build maybe one day a quantum computer, or at least do some kind of elementary demonstration of this. And the last thing, of course, is that it's kind of fun in itself, and it may shed light on something that I'm sure Jean-Michel talked about, which is what is and is there anything like a transition between the quantum and the classical world. So the idea would be you grow the size of your quantum system, still trying to maintain the coherence on the quantum aspect of it, and you look whether at some point, for example, the superposition principle breaks down. There is nothing in the theory that tells you that it should be valid at our scale. So we need to experience on this. So that's a few type of motivations that I could think of in order to justify why, as physicists, we are interested in building those artificial systems. Of course, to build these artificial systems as experimentalists, you need a platform. And there are actually many platforms that you can consider. There are the traditional platform that you all heard about in AMO physics, so neutral atoms in optical lattices. You had lectures on that last week. Trapped ions as well can be harnessed in a way that you can control the interactions. Photons themselves can be made interact. Actually, Anna will touch on that tomorrow. And there is also, I mean, it used to be new. Now it's no longer new, of course, because it's almost 15 years old. But all the category of artificial atoms. Okay, so you can, for example, take a vacancy in a diamond, and this looks exactly like a small hydrogen atom. So that's an example of an artificial atom. You can also trap an electron in a 3D structure to build a quantum dot. These also has bound state, and you can use them as an artificial atom. You have all the family of superconducting circuits, and what all those systems share is that in a way or another, you can always reduce them on certain degrees of freedom to two-level systems. So, I mean, it may be very difficult. I mean, in the case of a superconducting circuit, for example, this is just the sense of rotation of a current in a loop. You would say that if it rotates counterclockwise, it's up. If it in the other direction, it's down, for example. That's one way of encoding the information on those systems. So, and also what is important is that for all these systems, you can, after years of developments, address each of them. So do local manipulation on these systems, but also control their interactions in a way or another, which depends on the system, obviously. So if we go closer to the AMO platforms, this is kind of a landscape of the number of spins that people have handled, so the number of atoms that people have handled, also the range of the interactions that the atoms can experience. And you've got kind of two extreme corners. This is actually they're kind of merging, but basic idea is that you take trapped ions, for example. I mean, each ions can be controlled very, very precisely, but the drawback is that you can only connect a few of them, so typically a few tens. They're trying to grow the size of the system. On the extreme other scale, you have the atoms in the optical lattices. And the difference between those two systems is not the number, so this is about 100 to a few thousand of atoms, this is a few tens, is that here you can engineer the interaction in such a way that they are infinite range. Okay? While here in optical lattices, and this is of course changing, it has changed a lot over the last 5 years, but essentially the interaction is nearest neighbor interactions, based on the van der Waals interaction and the scattering S wave that Hugh explained to you this morning. Then there is a whole other type of categories here where you have polar molecules or magnetic atoms that you place in optical lattices. And there you see already appearing the idea of the dipole-dipole interactions. And so the system I will mainly focus on here is just ensemble of Rydberg atoms for which also we can vary, and it's still a dipole-dipole interaction, the power law of the interaction. Okay, so that will be mainly the story I'm going to talk about. But before we do all that, we will try to to understand a bit more what are those dipole-dipole interactions between atoms. So this is the outline of the 3 lectures. As usual, they are probably a bit too ambitious, but I mean, today it will be essentially blackboard lecture. So I will try to give you some hand-wavy arguments and so a bit more rigorous arguments about what those dipole-dipole interactions are and how you can reach the different regimes. And in particular, I will try to connect this 1/r cube with what Anna explained you this morning about these long-range interactions and this Green's function approach. In the second lecture, I will go basics of Rydberg physics, but Jean-Michel already introduced that. I will mainly focus on the interaction size of the Rydberg atoms, how we can engineer some kind of platform which is still original, although now there are like probably 13 constructions copying these things, but this is arrays of cold atoms. And I will show you how we can use these interactions in order to perform some quantum gates, for example. So that will be essentially tomorrow's lecture. And in the third lecture, I will give you some examples of many-body physics, especially of spin systems, using these Rydberg atoms. So that's the program, and let's see how far I can go. Okay, so let's start the first lecture of today with interactions. Actually, this is not, this is dipole-dipole interactions between atoms. Okay. All right, so the first thing we should remind us, and Anna already introduced that to you a bit this morning, but I will do it again in order to change a bit the point of view and also to put the emphasis on some other aspect. Let's look at what are atomic dipoles. So we all know that if you just take an atom, you solve the Schrödinger equation, and the outcome of the Schrödinger, I still need the thing in 1 minute, so, and then we can switch it off. So if you solve the Schrödinger equation, basically you know that the atoms, the atoms can be in different internal states. You've got an infinite series of them, okay, until the ionization threshold. They are parameterized by by many quantum numbers, but just to make things simple here, we'll only consider 2 of them. The principal quantum number n and the angular momentum L. Okay, so the wave functions are psi and L of R being the usual distance from the nucleus to the electron. Okay? Right, so now what is the dipole? The dipole of this structure, if there is only one electron, this is easy to write, this dipole is just QR. Of course, and I will not do that just because it's more annoying to deal with sum, but if you have a many electron atom, this would just be the sum of the charge of the electron, so Q is negative here, Ri, where Ri is the distance between the nucleus and the electron. Okay, so how do you make this thing an operator? Anna explained you how you do that. You just put hat on the thing, and it becomes quantum. D becomes D hat. And therefore, if it is an operator, it has matrix elements. Right. So let's look at the matrix element, N, L, D, N prime, L prime. Okay, I will call it, because I will use a lot this notation later, small d, n, L, n prime, L prime, which would be just a compact way to specify the matrix element. Okay, so the very important thing is to realize that for an atom, if I just calculate the momentum, the dipole moment in a given state, how much do I find? What is the answer? I mean, if I just take the same NL and the same NL, so basically, I take an eigenstate and I ask myself, what is the average dipole moment? It's 0. Why is it 0? Yeah. So for those of you who have forgotten the argument, you know that essentially this can be written in terms of wave function. This way. This is nothing than the modulus square of psi and L. A wave function of in an atom can have either odd or even parity. The square is always even. This is an odd operator, so if I change r in minus r, it exchanges the sign. Therefore, this integral is 0. I warn you, don't take that for granted. If I give you atoms in, or an electron in a quantum dot, this would not be true. okay, you would have a diagonal term in the dipole. It is just a very particular form or property of the Coulomb potential of an atom, which is that you've got this parity symmetry. But this is not always the case. You can confine an electron in a structure, for example, a box that you would have engineered or epitaxied or whatever, which does not have this property, in which case you do have permanent dipoles. But in an atom, you do not. If you were using a cold molecule, or a molecule, for example, KRB, you would also have a permanent dipole, just because you do not have this symmetry of the potential. So be careful. Do not take that for granted. There are underlying assumptions in these selection rules. Okay? So the second thing, obviously, is that if you do want this dipole matrix element to be non-zero, you need to change the parity of the wave function. So if you have dNL n prime L plus or minus 1, this is then different from 0. Okay, but this is a matrix element. This doesn't tell you at all what is the average dipole of a structure. Okay, so now, so once again, this is a very important property. And if you are in a given state, you do not have any permanent moment. And the dipole matrix element connecting two states is only non-zero if they have opposite parity. Please also do ask questions in case you have a... All right, so how do you construct a dipole? Well, if you want to construct a dipole, and what I mean by that is what? What I mean is that the average value of psi d psi, you want it to be non-zero. You need to place or to write psi as a superposition of several states. So let's say the first example, the simplest example. Let's just say that psi is nothing but the superposition of, in hydrogen atom, the psi 1s orbital and the psi 2p orbital. Just write it this way, okay? You know that because they would have different energy, there would be a term like this, and I will normalize in this way. So this is the state, which is a superposition of two states of different parities. Therefore, I can expect a moment, a dipole moment, an average dipole moment. The average dipole moment, if you calculate it, is just going to be given by, there is no dipole moment when you are in a given of these states, so it's only the cross term that will matter. So what you'll have at the end is psi 1s, psi 2p, cosine, I'm sorry, I just made a mistake, psi 1s d psi 2p cosine omega 0 t. That's the solution, which is exactly the one you are kind of expecting. So it's a you are in superposition. The superposition oscillates. The weight never changes as a function of time, and yet you've got an oscillating dipole. How can you understand that from the point of view of the electrons around the nucleus? So let's look at this small mathematical animation, if the thing works. So this is just a small movie here, where I have calculated, so just a very simple 1D model, but this is kind of, I find it enlightening to understand what is going on. Of course, you've got wave functions, right? So now, if I ask the question, what is, as a function of time, the probability of presence of the electron in space, what do you have? Well, you've got the wave function psi 1s plus the wave function psi 2p modulo square with a 1/2 plus the real part psi 1s psi 2p. So let's say the wave function are real, cosine omega 0 t. So you create a superposition of this orbital. There is the 1s orbital. Essentially, the 1s orbital, if you remember your AMO physics, it's an exponential, e to the minus r. You got the 2p orbital. It has a 0 at r equals 0. You do the superposition of these two things. This is what is written here. And now you let this superposition evolve as a function of time. There is this term. You take the modulus square of this, and you end up with an expression that oscillates. So how can you understand that? So this is a small movie that shows, and there is a bit of a problem with the animation. Sorry, this is the HDMI, which creates a problem. But so basically, you see that by superimposing two wave functions with a phase which varies as a function of time, the center of mass of the density of presence of the electron around the nucleus varies from one place to another. So this is why it creates a dipole. The minus charge oscillates back and forth with respect to the position of the nucleus. Okay, so this is the quantum version of a dipole. All right? Of course, there is a bit of a prime in what I told you. Do you have any question here? Do not be shy, so let me switch this thing. Okay. And so maybe now I can switch off the... All right, so... So now there is something where I've cheated a bit in my example, and where is it? So what is missing in my theory, of my elementary theory? Exactly. So I've assumed that at any time I'm always in a superposition, this plus this. Okay, but you know it cannot be the case because the atoms is going to decay at some point. Okay? So essentially, if I just plot what the atomic dipole should do, my intuition is telling me that it should do this. Okay, so it should decay with a decay constant which is essentially E to minus gamma to T. This would be my average dipole as a function of T. So essentially, everything I have showed you so far for my argument is this part. Okay, it's the very beginning. But then if I look at long time, my theory becomes to be inconsistent, essentially because the atoms has to decay to the ground state. So this brings me to the idea that how can we maintain a dipole? Well, a dipole, we have to drive it. Okay, so driven dipole, which is exactly what Anna explained to you this morning. So essentially, what I'm going to assume that among all the states of a real atom, I can isolate two of them, which must always be done if you have a combination of magnetic field, you tune the resonance perfectly close to the two states you want to discuss. So even an experimentalist can make an atom a two-level system. Okay, this is possible. Energy separation corresponding to a frequency omega, and on this thing, I'm going to send the light omega. The thing which you all know is that indeed this state can decay, and this is true for any state, by the way, even if they are high-lying states, obviously. And one formula which I'm going to use quite a lot is the fact that the line width of this transition is related to the matrix element connecting those two states. And it's given by Fermi-Golden rules, so I don't do the derivation, but the result is this. You've got E dg, the matrix element, k cube, 3 pi epsilon naught. Okay, this is how you relate the matrix element to the decay rate. So who has never seen this formula in his life? That's fine. Okay, so this comes from actually a not completely trivial derivation where you have to quantize the field, okay, and you couple this atom to the vacuum electric field. So I'm not going to do. Okay, it's not my fault. But basically, at the end of the day, there is something which is telling you that it's a process which is proportional to the square of the matrix element times something which is the vacuum density of state, which is essentially omega squared. Okay, very well. So now, how do you deal with the laser? I mean, you know that if you got spontaneous emission, unfortunately, your state cannot be a pure state. You need to adopt a density matrix approach because the system is not isolated any longer. So the density matrix is a useful way to do it. There are other ways like quantum jumps, but I mean this is certainly one which is very popular. So the density matrix rho, in the case of a two-level system, is just a 2 by 2 matrix, rho GG, rho EE, which corresponds to the population in the ground and excited state, and rho EG, rho GE, rho EG star. Okay? So why is it interesting? This because if I know the density matrix and I know them if I use the Bloch equation. So everyone has seen the Bloch equations here? It's fine. So the Bloch equation is just the equations that govern the rho G dot, rho EE dot, and rho EG dot. So I'm not going to write all of them. It's not interesting for what we want. But I'm just going to remind you a very important thing, which is that the average of the dipole can be directly connected, and this is once again what Anna told you this morning, to this density matrix just by saying that this is the trace of the density matrix times the dipole operator D. which in our case, and once again, bear that in mind, it's kind of important, is a non-diagonal operator, because I have assumed that there is no diagonal term in the sense that if I am in a state of a given parity, then I do not have any dipole moment. But once again, this is not always the case. It's true for atoms. This is not true for molecules or for electrons in complicated structures. Okay, and so now the thing which is interesting is the fact that this dipole moment, so let's make it scalar, right, so that I'm not annoyed by the vectorial notations. I'm assuming that the dipole is along one axis, is just, if you write everything, related to the coherence, so it's dEg, rho Eg, e to the minus omega t, and that's the real part of this. Okay? This is exactly what Anna has written to you this morning. The only thing I do here is I explicitly put the time dependence of the field outside of the density matrix. It's just a point of view. It's just because then this is a slowly varying envelope. And this slowly varying envelope has an interesting equation, which is rho Eg over dt is I omega naught minus omega minus gamma over 2 rho Eg plus I rho E minus rho Gg. Okay, so this is the Bloch equation for the coherence. And if this is for the coherence, it means that this is for the dipole. Okay? So now how do I make my dipole a classical dipole? I just assume that I hardly populate the system. So I'm in what is called the weak driving limit. And in this case, rho E minus rho Gg is essentially minus 1. So this is an important approximation. Robin will make extensive use of it during his lecture. Okay, so this is an exact expression if you assume the near resonant approximation. But apart from that, this is an exact expression. If you want to go to the quantum, to the classical, sorry, this is easy. You just take this equation and you just say the difference of population, so you neglect the population inversion. So if you do that, then you end up with an equation for the dipole, which is d dot of t, the average dipole, which is d over dt of is given by I omega minus omega naught. So don't be too picky on the sign. And for this thing, it's a matter of convention, and I never know which one I use. So minus gamma over 2 average of d plus I dg square e, the amplitude of the field, over 2. Yes, there should be an h bar, and that's it. So just for the notation here, I've used the usual notation that you all know, but there are conventions again, which is that h bar omega is minus dEg E0, the amplitude of the field, where the total field is E0 cosine omega t. Okay? All right, so that's all I wanted to say about the dipole. So this is the equations ruling the dipole. Okay, you can solve this thing. By the way, for those of you who know about the Lorentz model of the atom, which is this classical model that we learn about an electron which is elastically bound to the nucleus, this is exactly this equation. So this equation is a purely classical equation. Okay, so now let's move to the dipole-dipole interactions between two atoms. And I will first deal with the simplest case, which is the static case. What I mean static will become clearer at the end of the lecture, but this is essentially assuming that I do electrostatic only. Okay? So I want to derive the dipole-dipole Hamiltonian. So how do we do that? Well, we are just going to assume that we take two atoms, atom 1 and atom 2. To make things easy, once again, I will assume that this is essentially a nucleus and one electron. It's a bit simplistic, but okay. It kind of works to derive the Hamiltonian. You can always do the same by summing over all the electrons. And I will introduce two distances, R1 and R2. That corresponds to distance of electron 1 with respect to its nucleus, and electron 2 with respect to the other nucleus. Now I'm just going to call R the distance between the two nucleus, and essentially I'm going to write the Hamiltonian of this thing. The Hamiltonian for the electron is P1 square over 2m minus E square over R1. So here I will just use the notation once again, just not to be too annoying with the epsilon naught. I will use the fact that E square is Q square over 4 pi epsilon naught. So this is essentially the first electron bound to the nucleus. I obviously have the same thing for the second electron bound to the second nucleus. And I also have other terms. I can have the first electron bound, yes?
Yeah, a really stupid question.
No, there.
According to what you said, if I would do a pi pulse into the Rydberg state, I wouldn't have a dipole moment, right?
No, and you don't.
Okay, good.
So this is perfectly fine. There is no dipole moment. Hopefully, the end of the lecture will kind of make you a bit happier because
What you usually hear is that when you hear that it has a dipole moment.
it's totally wrong.
And that, okay. Then I'm happy.
Okay. You say a lot of things to make things a bit simpler. Sometimes you oversimplify. This is one example. Then what I have is the attraction of the first electron by the nucleus of the second one. So R minus R1 minus E square R minus R2. And you also have the repulsion between the electrons. So you have R minus R1 minus R2. And there is no approximation. As far as I'm concerned for the electrostatic problem, this is all true. Now we do a Taylor expansion, which of course I'm certainly not going to do, which is a bit annoying. So what you're assuming is that the Ri over R is much smaller than 1. So what you're assuming is that an atom is much smaller than the interparticle distance. This is the condition under which you can derive this Hamiltonian. And so at the end of the day, you end up with the dipole-dipole Hamiltonian. So I only keep this part, which you can write in the form that I'm sure that most of you have already encountered. Divided by R cubed. Okay? Who has never seen that in his life, ever? Okay. Right, so nothing special to say about that, apart from the fact that if I want to quantize, I again put hats on this thing. And I also to look a bit more closely about the Hilbert space of the problem. So the quantification, this Hamiltonian, becomes, of course, an operator, where all the dipole D1, D2 are operators as well. So you've got D1 is an operator, D2 is an operator. Okay, I'm assuming in all this that the atoms are pinned in space and frozen. And this is an important approximation as well that people in molecular physics quite often have to look a bit more in detail. But okay. So frozen is space. So now, of course, I have two atoms. Therefore, the Hilbert space is the tensor product of the Hilbert space of the first atom by the second atom. So a basis which I will need in order to write the matrix element of this Hamiltonian is the tensor product NL, N prime, L prime. So these will be called pair states, which are like the states of a pair of atoms. Okay? And quite often I will use a simplification notation NL, N prime, L prime. Very well. So, any questions so far? So how good the approximation of the dipole interaction? This is, we do physics, not math. So we always have to remember that the size of an atom, delta R, is on the order of the Bohr radius, at least in the ground state. Things are a bit different in Rydberg state. So typically 0.1 nanometer. And usually if you just take R, which is 1, 2, or larger than 1 nanometer, this becomes a very good approximation. For the following reason is that the thing that remains here is in the fourth order, actually. Okay, so you see that very rapidly you have a pretty good accuracy in the calculation. For Rydberg atoms that are much larger, you need to be careful, because it will certainly be completely wrong at this scale, and you need to make them further apart. All right. So now let's look at a toy model. And this toy model is going to be very interesting because we're going to see appearing the two kinds of interaction that two atoms can go when only the dipole-dipole interaction is concerned, the resonant dipole-dipole and the van der Waals interaction. So let's take two-level atoms. Each will have ground and excited state G and E, separated in energy by the same, so I do exactly the same assumption that Anna did this morning, identical atom, and they are separated by a distance r. Okay? And so I will try to write the full Hamiltonian for this problem and to solve it. So let's plot the energy diagram for two atoms. I can, of course, have either the two atoms in the ground state. Or I can have one atom, so this will be, let's say, the energy 0. Or I can have one atom in the excited state or the other one. So I have two states that are degenerate, EG and GE. Okay? And so now I have the third state, EE. Energy 2 h bar omega 0. And here there is no interaction, right? And so I'm assuming that I switched off HDD is 0 for this drawing. Let's write now the full Hamiltonian, H total. And I will write it in the basis EE, GE, EG, GG. Okay, I will just order the basis in a slightly different way. I will just say this is GG, EE, EG, GE in this particular order. I do it on purpose. So let's try to fill that in. I mean, the diagonal term, this is kind of easy. This would be 0, h bar omega 0, h bar omega 0, 2 h bar omega 0. Okay? What about the couplings? Well, I mean, I have the couplings between this guy and this guy, coupling between this guy and these guys, the same. And I have also the coupling between these ones. So let's look at the matrix element. And actually, I lied completely. What I've written right now is totally wrong. So why is it wrong? Yes, exactly. So this is 0, 0, 0, 0. Okay? So I want to couple, let's say, EG with my dipole Hamiltonian, which I will simplify by writing it d1, d2 over r cubed. Of course, it has to be understood that, in principle, I should go to the full vectorial stub, but let's not worry too much about that. So basically, what I have is E d1 G, G d2 E over r cubed. So basically, the two states EG and GE are directly coupled by the dipole interaction. Okay? So this gives me d EG squared over r cubed. I'm dropping the 4 pi epsilon naught, the same argument as. So now, what I know is that I can already place here d square, I'm sorry about that, with the order of the basis I have taken, it's 2 h bar omega naught, h bar omega naught, h bar omega naught. Okay, because I place G and E, and I place EG and GE. E square EG over r cube, d square EG over r cube. And it will be 0 for all the others. But I also have a matrix element between the states EE and GG. And this is the same. It's E, 1G, E, E2G. Okay, so I also have two terms here. E squared over r cubed. So actually, it's a kind of interesting way to write this matrix, because now it's a block diagonal matrix. I have two matrices to look at. And in these two matrices, unfortunately, or fortunately, I don't know, but it's just a fact, I cannot treat them in the same way. This one, essentially, for most atoms you would encounter, this is an optical transition. And even if it's a microwave, it doesn't matter. Therefore, this term is most of the time extremely small with respect to this one. So I will use perturbation theory in order to look at this part of the Hamiltonian. For this one, I cannot do that because I have two degenerate states. So I need to diagonalize the matrix. But this is a 2 by 2 matrix, so it shouldn't be too hard to do. So let's look first at the block which will actually lead to the van der Waals block. Oops, so it will be a catastrophe now. Okay, so the van der Waals block is 0 d square over r cube, dg square over r cube, 2 h bar omega naught. And for this one, I'm going to assume, which is always the case, that this is much larger than this. We could run numbers, but it will come later, but this is always a very good approximation. And therefore, we know what are the solutions to this matrix in this case. So I'm not going to do it, but you know how to deal that in perturbation theory. Essentially, the ground state, so delta Eg, is going to be shifted by an amount which is the square of the matrix element divided by the diagonal term. So d Eg square over r cube square divided by 2h bar omega 0. There will be a minus sign for this one. That corresponds to the state psi gg, which is the initial gg state, plus d Eg square divided by 2h bar omega naught EE. This is clear for everyone. They think I'm not going too fast. Yes, I'm just assuming that you've seen that once in your life, and when you've got an array, a matrix which is this way, you can immediately write what is the energy shift. This is v square over delta, plus or minus. Okay. Second thing, and of course, sorry, and the state, the new eigenstate are essentially the first one with a small perturbation, which is the square of the matrix element divided by delta. So once again, bear in mind that everything I'm telling you, it's not only that I'm not trying to be rigorous, as you can already see, but I'm trying to give you also some ideas of things you will encounter all the time when you discuss physics with your colleagues. So those are all the kind of arguments that you need to get used to for doing your PhD. So it's not necessarily rigorous, but this is very important to have all these orders of magnitude in mind. Okay, so delta EE is what? This is going to be 2h bar naught, the initial energy, which is going to be perturbed by the same but with an opposite sign. dg square over r cube divided by 2h bar omega 0. And this is beautiful. I have the van der Waals interaction. This is the 1 over r6 interaction that shows up here immediately. This is the 1 over r6 energy shift, 1 over r6 energy shift, which is the van der Waals interaction. So this is how the van der Waals interaction arises. And the thing which is also interesting is to see that essentially, as we are in the approximation that dEg square over 2h bar naught is very small, the state is hardly admixed. So essentially, you can say that the only influence of the dipole-dipole interaction is to shift the energy level without hardly touching the initial state. Okay, so psi, so energy shift, so van der Waals is just energy shift of initial state. Initial state meaning, once again, that I neglect the small admixture that I have here with the other state. Yeah, minus sign so that they are orthogonal, sorry. Questions so far? Stupidly enough, I just erased the Hamiltonian. So let's go back now to the second part of the Hamiltonian. The second part of the Hamiltonian is the, let's call it the resonant interaction block. So this is this block, energy So in the basis EGG of this first side, doesn't really matter. So we know how to diagonalize that. We've got two energies plus, two eigenstates and eigenenergies. EG plus G, which have an energy which is h bar omega naught plus dEg square over r cube. So this time the interaction arises at first order. There is no perturbation theory. So this is E plus. And minus is 1 over root 2 Eg minus Ge with an energy which is the same dEg over r cube. And those two states, for a reason that will become a bit clearer in half an hour, are called subradiant and superradiant states. This is what is called the superradiant state. This is what is called the subradiant state. And Anna is going to spend a lot of time on this today and next week, and probably Robin will spend, because he's Mr. Subradiant, so he will be the one talking a lot about this, I'm sure. Okay, so if we just try to sum up everything we've seen here, it's actually not too bad for a toy model. If I summarize everything we've seen, we've started from those states, separated in energy Sorry? I've been too fast, so you want me to... That's actually maybe... C'est bon? Fine? Okay, so what I'm going to plot now are the energies that we found. C'est bon? It's all right now, it can go down? Okay, fine. And we'll look at that as a function of the interparticle distance. So what have we found? We found that for the excited state, essentially you've got something of the forms 1 over R6, so C6 over R6. For the ground state, same thing, but with opposite sign. And for the intermediate state, we split the degeneracy with two terms, T3 over R3. That corresponds to the EG plus G, EG minus G. The exact position of up and down depends on the angle, so I don't want to go into that. This is not the ingredient. Is it the truth? Yes, it is. For those of you who remind a bit about their chemistry, so those are the potential curve of the rubidium-2 molecules, two identical atoms, so calculated by real serious guys, so Olivier Dulieu, actually who work with Goulven. And you see the gross picture of what I showed you here. It's just a bit more complicated because, of course, the atoms do not only have two levels, so this is why it looks so messy. But at the end of the day, you recognize the trends. 1 over R6, splitting 1 over R cube. And here I don't have on this graph the 5p, 5p, but if I add it, it would be doing this. So indeed, this very small toy model already tells you everything you need to know about the two kinds of interactions that the dipole-dipole Hamiltonian can lead to. The resonant dipole-dipole interactions, and I was just talking about you a minute ago, and the resonant dipole-dipole interaction and the van der Waals. So they all come for free in this toy model. So this is an important model to keep in mind. Okay, any questions so far? Let's do a bit of numerics, just to get orders of magnitude. So let's look at the plus and minus dEg square over r cube. I mean, of course, none of you know by heart the value of dEg for its beloved atom. But the kind of thing that most of experimentalists know is the line width of the transition they are considering. And I remind you the formula I had written with the Fermi-Golden's rule that h bar gamma is dEg square omega cube, k cube, over 3 pi epsilon naught. So if I wanted to be completely correct here, I remind you that I would have to put the 1 over 4 pi epsilon naught, which I just dropped so that it's not too heavy in the writing. So I can express everything in terms of gamma. So therefore, the energy splitting that you have here is, so the plus or minus, it becomes a plus or minus some coefficient, which are 3/4, it doesn't really matter, divided by kr cube. So you see that at the end of the day, this is kind of obvious to calculate what this interaction strength is. Just take a transition which has a gamma in the order of 10 megahertz, like cesium. Or you could take, for example, strontium on the weak transition on a few kilohertz or whatever. But let's take this. K is 2 pi over lambda. Okay, lambda, let's say it's 1 micrometer, and let's put two atoms separated by 1 micrometer. Kr is 1. Okay, therefore, the energy splitting is just the line width of the transition. So energy splitting, delta E, is twice h bar gamma, the line width, when R is on the order of 1 over k. Okay, so you see this is actually a very large interaction strength. At 1 micrometer, this resonant dipole-dipole is able to, it's actually not 1 micrometer, it's 1 micrometer divided by 2 pi, which is actually the pain in the butt for the experimentalists, the 2 pi. It should not have been invented because separating two atoms by 1 micrometer you can do, by 100 nanometer, this is really a nuisance for an experimentalist. Okay, so we've got the orders of magnitude for the resonant. What about the van der Waals? We know it has to be much smaller, and we will indeed find that it's much smaller. Van der Waals is what? 1 over 4 pi epsilon naught dEg over r cube square divided by 2 h bar omega naught. Once again, I dropped all the 2's and everything, so this is what? Well, this is roughly speaking h bar gamma square divided by 2 h bar omega naught. Therefore, this is h bar gamma in energy, gamma over omega naught. Gamma 10 megahertz, omega naught, it's an optical transition, 300 terahertz. Therefore, indeed, the van der Waals, as we know, is much smaller at 1 over k distance. Okay? So at r equal 1 over k, so we find that this is essentially van der Waals is on the order gamma 10 megahertz times the ratio of 10 megahertz divided by 300 terahertz. So this is significantly smaller. Actually, so this is 10 to the 7, 3 10 to the 14, so it's gamma 10 to the minus 7. So it's typically 1 hertz. And if you look in the literature, what is the van der Waals interaction at this distance, this is what you find. So I mean, once again, this model is kind of very useful because it allows you to find every orders of magnitude of the atom, the interactions between two atoms. Okay? Questions? No questions? Oops, sorry. All right, so just to finish off, this was a toy model, and already it's a pretty fruitful one. Let's go to real atom, which is to say multi-level atom. So of course, all what we found you should recover, but unfortunately the states are many more than just 2. So we need to remember that essentially that you start from pair state. And let's look, for example, at what is the van der Waals interaction between two atoms in a given state, NL and NL. I do not specify what are N. They may be the ground state, they may be the Rydberg state, doesn't matter. But the thing I know is that there will be many states around. all with opposite parity for each the L and the L prime. So we'll have N prime, L prime, N second, L second, and I have plenty of them. Okay? Each will be coupled by a matrix element, which is exactly the one we've written here, but it's just a bit more complication in terms of notation. It's NL, N prime, L prime, times D, N, L, N second, L second, over R cubed. This is the matrix element that connects that. And it's different, of course, for each of those states. So if I use perturbation theory, I can calculate the van der Waals shift. So delta E of the NL state is what? I mean, this could be the first order shift. In perturbation theory. But this one, we said it has to be 0 because you do not have any dipole moment when you are in a given state, eigenstate. And you need to sum over N prime, L prime, N second, L second. Of course, once again, I insist on the fact that L prime has to be equal to L plus or minus 1, and L second, L plus or minus 1 as well to fulfill the selection rules. Otherwise, you do not have any dipole moment that couples. And it's just this kind of annoying expression that you learn in perturbation theory. So let me write it. Divided by the difference in the energy and I forgot something important, which is the square. I mean, this is nothing but what we've already done. Huh? It's just that it's a multi-level problem now. You recognize the DEG square over R cube square and the difference of energy between the two states you're considering. So this is what you find in the literature under the form C6 over R6. So it's a bit annoying, and you need to know all these dipole moments in order to calculate this. And people have done that a lot in the past, and it's usually a good idea to have an order of magnitude what's going on. Quite often, you only have a few transitions that are close enough and that allow you, and that dominates in the sum. So it doesn't mean that this is it's an infinite sum, but essentially 10 terms dominate for Rydberg state around n equal 50. You also find something which is interesting in this expression. If NL is the ground state of the atom, necessarily the denominator is negative. This is the lowest energy state. All the other states have to be larger. Therefore, there is a minus sign here. So you find that in the ground state, it's only repulsive van der Waals interaction. I mean, we know that, but it's good to find that our formalism gives up. So En L minus En prime L prime minus En second L second is negative, and hence delta van der Waals of ground state is always a negative shift. This is not always the case for a Rydberg state. For a Rydberg, you can have positive or negative. Okay? Questions? No? All right. Of course, we are in the 21st century. No one applies perturbation theory any longer. Everyone goes on a computer, and people have worked for you, and you've got online calculators for all these interactions. You learn nothing because someone has done the job for you, so it's good to know everything I've told you, but it's much faster and accurate to go this way, to the computer. So you can find actually for the Rydberg atoms and for the alkali Rydberg atoms, I should say that for group 2 atoms, like 2 electron atoms, this is still, I'm not going to say an open question because, I mean, of course, people have calculated, but with much less accuracy. Okay, so don't take for granted that everyone knows since 100 years how to calculate the C6 coefficient of 2 dysprosium atoms, for example. Okay, this is a hard problem. But for alkali, you can have test wave functions, and therefore it's possible to build those kind of codes. So just to show you what it looks like, so you can go on the internet and download this app, which will look like this. So this is, for example, the interaction energy. So this is the distance. This is the energy. You enter the principal quantum number. I've taken n equals 60. The L, so L equals 0 is an S state, and you need to specify the J, so it has a spin, so let's say J equals 1/2. And you have this very nice, so together with this line, which is the fit by C6 over R6. So indeed, it works pretty well. Let's put, for example, now L equals 2, so 60D states, okay? And I'm going to take 3/2 and 3/2. I mean, of course, you can do everything. The thing calculates, and you see that already it's much more messier. You do have some van der Waals curve, but I mean, this is kind of an approximation of van der Waals, but things are more complicated, sure. It's the full diagonalization. It doesn't invalidate anything I've told you. I'm just telling you that indeed, those potential curves are more complicated. We can also go to 60S, so let's take 0 and 60p, and see whether we have the exchange interaction. Oops. You see, you need to be smart to do that as well, which is you need to know a bit of AMO physics. Merci Jean-Michel. So I also need to say that I cannot have 3/2 for this. And you do see, indeed, this spacing, which is essentially the C3 over R3. But if you go to too close distance, this breaks down again, okay, because other states enter in the problem. Okay, so you see, this is a nice way to kind of play with the interactions between two atoms, at least in the static case. Is that clear? Do you have any questions so far? No? Bon. Sure.
What ends can I put in? I mean, like, is there a problem with the calculation once I go to low?
Yes, because then this thing doesn't estimate properly the wave function. So I haven't tested the thing down to n equal 5, but I think that above 10 it starts to be very, very good. Okay, and just to give, let's make a try. Someone told me that if you go, let's say, to low enough state, the C6 should be negative. Let's see whether this is true. So negative that you don't even, sorry, 0. It's just too small. It's even too small. Bon, okay, so there is something, so it's, okay. You have to play with it to find that it's negative. Okay, so that's all I wanted to tell you about this, and now I will try to connect to what Anna told you this morning, and that she will derive completely rigorously following this lecture. So stay tuned, as we say. So let me switch off this thing. Turn on. So unfortunately, this is the hardest part of the lecture. It's very badly designed, as you can tell, because it comes at the end. So part number 3, resonant dipole interaction beyond the static case. Okay, so what I've assumed when I derived what I've derived so far is just, of course, an atom has a size A0, which was much smaller than R. And this is certainly true for most atoms. But I also introduced this toy model, being extremely careful never to talk about spontaneous emission. Okay? So I have my excited ground, so we've diagonalized the full thing, no problem. There is one thing I forgot to mention, is that indeed this thing can decay. And when it decays, it emits a field, and this field has a wavelength lambda. So lambda somehow has to appear in my description. I have one energy scale, one length scale, A0. I now have another one. What do I do with it? Okay, and this is exactly what I'm going to discuss now. So at the end of the day, the idea is reasonably simple, and I will use again the classical idea that Anna introduced this morning, which is to say, if I just drive my atom, so I just send, so So I have an atom here, an atom here. I just drive this atom with a laser, which is oscillating at a frequency omega. Of course, I'm going to induce two dipoles. Let's assume, and that's only an approximation, that can be true, but let's assume that the dipole can only oscillate along the z-axis. It's always possible, and if you polarize with the magnetic field or so on, you can select the selection so that this is the case. For those of you who are interested in, the only thing that it is telling you is that the polarizability of the atom is a tensor, which is highly anisotropic. Alpha being this one. Okay? This is an assumption, and once again, you can do it in the lab. It's possible. All right, so now we know what is the problem, because I mean, this thing is an oscillating dipole. I've written to you the equation that governs this dipole. You remember this d dot is equal to I delta minus omega blah blah thing. I'm going to write it again later. But at the end of the day, what this is telling me that this field radiates, this dipole radiates a field. Therefore, there is a field here that drives also the second dipole. Therefore, this is again what Anna said this morning. This dipole is driven by two things: the external field and the field of the first dipole. Okay? And we're going to write what is the field of the first dipole. And so this is the thing that the theorists consider trivial, which is the vacuum Green's function. Okay? At the end of the day, if you open your Jackson or whatever ENM textbook, you find that the Z component, so Z being, because as I impose the electric field, the dipole to oscillate only along Z, the only thing I need to consider is the EZ component, is given by d1 of t over 4 pi epsilon naught times 1, so let me write it correctly, this expression, 1 over r cubed minus IKR. So who has never ever seen in his life this expression? Okay, so this is just the field radiated by an oscillating dipole, but you include all the near field and far field terms. Okay? So things are a bit more complicated. I can always write it exactly as Anna said this morning, as a Green's function times a dipole. But here I do everything scalar, just to simplify. So at the end of the day, if you wanted to connect with what Anna said, this would be the ZZ components of your Green tensor, d1 of t, where the Green function, the Green tensor, is just this. And we may discuss about the factor mu naught, epsilon naught. It's just convention, right? So let's not bother too much about that. So of course now, if we have this field, there is an interaction energy between the dipole and the field. Therefore, I would have an average interaction, which is d1, and if I use complex notation, E1 over 2, which is the EZ component. And this is 1 over 2. And if you write everything, what you have is d1 square of t, 4 pi epsilon naught, k cube, I'm going to write it slightly differently, 1 over kr cube, I over kr square, 3 cosine square minus 1 plus 1 over kr sine square theta. Okay, so all classical physics. But I mean, you can't do quantum optics if you don't know classical physics. It's impossible. You start always from the Maxwell's equation, so this is classical ENM. All right, so now let's introduce quantum mechanics in this thing, just by looking at the only quantum part in my thing, which is the dipole itself. So this dipole, d1 square t, what it is actually, this is my d of t square, which I can rewrite as dEg squared times the modulus square of the coherence, rho Eg squared. Yeah, because we said that what links the average of the dipole is the square of the, the average of the dipole is linked directly to the coherence rho Eg times the dipole matrix element. Okay, so at the end of the day, this expression, I can look at it in a slightly different way. And before I do that, I remind you one property of the density matrix that you may or may not have seen. I keep on forgetting it, so I will not put the blame on you, but there is an important relation between the coherence and the population in the density matrix, which is that the product of the population is equal to the square of the coherence, a two-level system. So now, if I am in the low saturation limit, which is to say rho E, which is much less than 1, rho G is just rho GG is just 1, and therefore the coherence square is nothing but the population. This is actually a very profound fact, and it allows for those of you to calculate the Molo triplet and all these things. So it's very profound quantum optics relation, this thing. We're not going to much about towards that. But basically what this means, again, I can rewrite this entire expression in the following way. dg square over 4 pi epsilon naught k cube e to the I kr. I do not rewrite what is in the bracket, it's not important, times the population in the excited state. So now I have a term which I will call VDD, and which is totally independent of whether you have light or not. It's something which is a property of the transition only and the distance at which you look at. Okay? And where does the light come from? Which is telling you that if you have no light, you've got no interaction. You need to find this fact. It's just this is the population that you put in the excited state of the system. And what we're going to do now is to interpret this VDD as the matrix element of the Hermitian operator. So this is exactly the Hermitian operator, the Hermitian Hamiltonian that Anna wrote at the end of her lecture this morning, and that she will derive rigorously in the next lecture. Okay? So the bottom line, the thing I'm trying to get at here is do not get mixed between what are the matrix element and what is the average value of the operators, because if you do so, the discussions are endless and totally pointless, because people are not talking about the same thing. You may have a matrix element between state EG and GE, but you may not have any interaction just because there is no light that you send on the system. Okay? So be very careful about that. Okay, so in order to make the thing a bit more explicit, what I'll need, and so this is the very experimentalist point of view. The rule truth with the horror of the Green function and the Markov approximation will be done next, okay? So this is the hand-wavy argument. Let's go back to classical, and let's introduce the idea of subradiant and superradiant states. How do we do that? Let's go back to the equations that I have written an hour ago now, which is the equation that governs the evolution of a dipole. D1, so this is classical, is I, let's call it delta, the difference omega minus omega naught, minus gamma over 2, D1, plus, if you remember correctly, I had something which was dg square over 2h bar, if I remember correctly, times E naught. But this is just the case of one atom driven by the laser. But this is not what I have here. I have one dipole driven by the laser and by the field radiated by the other ones. So what I need to add here is precisely my Green function, gz_d2. Which in my very naive approximation, all this is scalar, right? Because I don't want to deal with the tensor part of the thing. And then I write the same, obviously, for D2. This is I delta, driven by the laser. But also by the ZZ field. Sorry, by the field radiated by the first dipole. So this is a set of coupled equations that you will hear a lot in Romans Kaiser's lecture. Just a simpler case where you only have two atoms. But of course, you can do the full theory when you have all the other dipoles. Here, you replace that by a sum. And then you've got n equations, so just a mess. You need to calculate them. But for 2, there is a very easy way to diagonalize this thing. let's introduce d plus or minus, which is equal to d1 plus or minus d2 over root 2. If you calculate now the evolution, sorry, there is one thing I want to emphasize again. This gz is a complex number. Okay, this is very important because I will use that. Why is it a complex number? Because of this and because of this. Okay, so if you do all that, you will find out that you've got two decoupled equations. D plus, which is I delta and minus, sorry, D plus and minus. Okay, plus I. So here I should have been slightly more careful, sorry about that. Let's make sure, I mean, the field is not the same whether you are an atom 1 or atom 2. If they are not located exactly on top of each other, there is no reason why those two fields should have the same amplitude. Especially you got a phase factor if you send plane wave. So you would have an E naught 1 over root 2. Okay? I mean, you have to believe me. You do the few algebra, and at the end of the day, you've got this with delta omega, which is the shift with respect to the bare frequency, and which is precisely given by the real part of this VDD expression here. And you have gamma plus and minus, which is gamma of the bare atom, plus or minus, yes, sorry, actually, delta is plus or minus the imaginary part of VDD. So now, what am I telling you? I'm telling you that I cannot think of the two dipoles are independent. They're actually a composite object where the two dipoles can either oscillate in phase or in phase opposition. For the situation where they oscillate in phase opposition, you will have a shift in energy, which is actually the real part of this, which is independent on the fact that you drive or you do not drive. This is just a property of the transition. And you also modify the lifetime or the decay rate of the atom. Okay? So, maybe I will switch that on again. So the one where usually you've got a minus is called a subradiant state because it has a lifetime which is much longer. So I'm going to show you what they look like. Oops. So just take, of course it's complicated because it depends on the angle and so on and so forth. But so basically, if you just take two dipoles like this, what you find is that the real part, which is represented here, I mean, of course, at short distance, it needs to be 1 over r cubed that dominates. But at long distance, you've got some oscillatory behavior of the energy. So the long range term, the 1 over r, gives rise to this oscillatory behavior because you've got sine kr over kr. What about the lifetime, so the decay rate? Well, you see that if you try to put the two atoms very close to each other, one of the two states has 0 decay rate. This is the subradiant state. It corresponds to the two dipoles oscillating in phase opposition. Therefore, the two fields that are scattered interfere destructively. Therefore, they do not radiate. While here, they interfere constructively. So this is the superradiant state. It has 2 gamma of line weight. Okay? So this is exactly what we find here. Okay, of course, it depends on the orientation, so I've just taken another one. So this one, the gross pictures are still valid, but you see that the details are different. Okay, because you've got the cosine square theta and so on. Okay. So one thing I would like to show you now is, of course, you've got two regimes. And there is the near field regime, and there is the far field regime. This is the expression of VDD. Okay? the one which does not depend whether you send light or not, doesn't matter. You'll see in a minute how it comes into play. Of course, if I work in a regime where the two atoms are much closer than the wavelength of light, essentially I can completely neglect the kr square, especially the I, the sine kr, the 1 over kr, and also the e to the I kr is just 1. So what do I recover? Just the static dipole interaction, which is the one that we've dealt with in the first part of the lecture. The atoms are too close with respect to the wavelength, so it's electrostatic that matters. I recover all that. And it's the very same expression. And of course, in the case of light scattering, so it will be the lecture of Anna and also of Robin, you usually work in a regime where the optical transition you are dealing with in the micrometer range, so it's very hard to have the atoms close to each other. So now you have to take into account all the terms. But there is a good thing for you, is that then the Hamiltonian, or actually this term, is a complex number, which is indicating the fact that the system scatters light. So you can read the light and do something for quantum optics. You cannot do quantum optics with Rydberg just by monitoring the photons. And why is that? Because you've got very different length scale for the optical wavelength. If you are in an optical transition, the typical optical transition is in the micrometer region or lower, whatever. So divided by 2 pi, which is 1 over k, this corresponds to 100 nanometer. So it's actually very hard to place atoms so close to each other. So usually when you do dipole-dipole interaction in the optical regime, you need to consider all the terms. But if you are in the Rydberg manifold, you have two nearby states, a very highly excited state. And typically, the wavelength of the transition between two nearby states is in the centimeter region. So if you place two atoms at 10 micrometer, you are in the near field regime, and by a lot. Because then Kr is essentially 1, it's 10 to minus 3, if you wish. So this term completely blows up. Okay? But it also means that in this case, if you are in the near field, you can completely ignore, so near field, you've got the dipole-dipole is on the order of h bar gamma over kr cube. And this term is much, much larger than h bar gamma. So you can completely ignore the spontaneous emission and therefore do as if it was a properly coherent spin interaction, as I'm going to show you in a minute. Okay, so you see that I wanted to show you that because, I mean, sometimes when you read reviews, of course, you've got the reviews on light dipole, you've got the reviews on the Rydbergs. It's all the same thing in different regimes. At the end of the day, this is all the same underlying dipole-dipole interactions, but when you take into account the possibility that the photons comes into play. It's just that for microwave phantom for the Rydberg, essentially the spontaneous emission is completely negligible with respect to the strength of the interactions. You do not care about it. In the dipole limit, you do need to care about this being usually on the same order as this. Okay, and this is why you can do quantum optics with it, because you have access to the photons. Okay, just to briefly finish off, let me give you the quantum interpretation of all this so that I introduce actually Anna's lecture. Juste rallumer la lumière. Okay. Actually, if I look at d1 d plus of a square root of 2, and I go back to the quantum, what this is really about, this is the average value of d plus and d minus, which is nothing but gg, d1 plus d2, 1 over root 2, eg minus ge, sorry, plus or minus. This is what you have. So what I want to say now is that I cannot consider my two atoms as independent, but actually this dipole corresponds to the dipole moment of the global object of the two atoms placed in the state Eg plus Gz plus Ge, or Eg, Eg minus Ge. I want to say, once again, let's do the drawing that we've done several times together already. You would have the gamma plus, you would have the gamma minus, Okay, so this is the super radiant state. This corresponds, if I calculate the average dipole, the matrix element between those two things, GG state plus, this corresponds to my D1 plus D2. This corresponds to the dipole GG, D1 plus D2, minus. So what this does is that the eigenstate of the systems are entangled state. Okay? You cannot think of an atom independently of the other ones. And you can view this picture in a slightly different way. You can say, well, but this is exactly the eigenenergy of an Hamiltonian, which would be VDD sigma plus A sigma minus B plus sigma A sigma B plus, which is the flip-flop interaction that Anna talked to you about. And this is the very same VDD we've derived completely classically. It's just that this is a non-Hermitian Hamiltonian. And it's perfectly valid. You can use a non-Hermitian Hamiltonian, provided the fact the system is not too excited or you work in a quantum jump approach. But Anna will tell you more about that. See, if I want to diagonalize this Hamiltonian, I would have omega 0 VDD, which is a complex number h bar omega 0, in the EG G basis. And once again, I would have as eigenstate EG plus or minus GE with eigenenergies omega naught plus or minus VDD. But they have now an imaginary part, okay? Which signs the fact that the system cannot stay forever in the excited state because it has to decay. So this is what is called an effective Hamiltonian approach. This is actually very important for those of you who have never heard about that. I do encourage you that you open textbook on this because this is something which is very useful to do intuitive reasoning. And also for those of you doing quantum Monte Carlo, you use that all the time, the quantum jump trajectories. Okay, just to finish off, I have 4 minutes left. Just want to show you an experiment. So do you have any questions so far? No? So for a very long time, it was actually pretty heroic to try to measure that. And a few groups managed to do that. At least in a controlled way. I mean, okay, now things have changed a bit. But I mean, in the around 2000, so in 96, those guys, so Deve and Browaeys, did a very beautiful experiment, but just took 2 ions. Okay, and they could vary the distance between the 2 ions. But of course, the ions, they repel each other, so you cannot place them very close to each other. And yet, for 2 ions separated by 1.5 micrometer, which they could do, they did measure that if they excite these ions, their lifetime would be modified. And it has to be modified because of exactly this gamma plus and minus that we've seen. So this is part of this curve, which is the sine k, I mean this gamma plus curve as a function of kr that they measured. And they were able to change the distance and see that indeed this pair of ions did not radiate the same way as the ions taken independently. Okay? And there was a second very nice experiment done by Weitz and Ogdar. I don't remember where actually, but it doesn't matter. So around 2002. So where he took 2 molecules, and those molecules, they could really place them on substrate and very close to each other. So typically in the near field. And they were able to see, to do the spectroscopy on this system, and to observe that indeed one of the line is narrower than the other one. Forget about this one, which is a 2-photon process. And this one is the subradiant line, so the one which is narrower, subradiant. It's not exactly 0, as it should be if they were placed right on top of each other, because they are not. And here this is the superradiant light, which is slightly larger than it should be if they were interrogated, a single molecule. So this is one of the very first time people had seen that. I mean, now people have gained a lot of maturity on the control of individual systems, so those experiments have been done in different ways, and so people see that obviously again. Okay, I think I will stop here for today, and tomorrow then we'll do mainly Rydberg from there. Thank you.
Actually, in the last experiment you saw in the show, why don't you expect a different, like intensity or volumeric intensity for the separate?
Sorry, the difference in amplitude. It's a problem, to tell you the truth, there is. It's a problem of resolution of the spectroscopy. This one is much narrower and should go higher. Okay, so the resolution makes it hard to actually see that. Because you're completely right. I mean, if I plot those things, in principle, it should be like this. Okay. But I mean, you have to be a bit careful and look in the details of how they did the excitation in the system as well.
But then if you place yourself precisely at the frequency, then you have a higher intensity for the super-radiant than for the super-radiant phase. If you place yourself exactly in resonance.
Well, yeah, but it depends how you excite them. Because you remember when I wrote the coupled dipole equations, when you diagonalize, they are not driven by the same field. There is an E naught plus E naught 1 plus E naught 2 and E naught 1 minus E naught 2. So the coupling is also different. So experimentally, this is a nightmare because you scan your frequency, and the amplitude, the Rabi frequency of the two atoms changes when you change also the interparticle distance. So I mean, there are many things that are hard to keep constant in this. The only thing which is constant is the line width of the line. Its amplitude is very hard to compare. It can be compared to theory, but it means you cannot keep it constant.